one issue that I have is okay. So first, let me tell you what we're going to do today. Previously, we did some stuff with the cantilever, so you guys are very familiar with that. So the natural thing is to see how a cantilever is simulated in something like COMSOL. We're going to do other things too, but I'm trying to you know, do a smooth transition between things. Now, we have access to two types of COMSOL. We have COMSOL version 3.5, and we have COMSOL version 5.5. There's a huge difference between the two. um, and um, and version 5.5 is what we're trying to get the entire school to buy. Remember, so we're going to be using that because that's like the latest and greatest version. The old version, I've just been using it a long time. So, but the cool thing about the old version is that it doesn't have all the bells and whistles. You might think that's a bad thing, but sometimes having, just the bare necessities is, just to get the things you need to get done is all you need. And so there's a lower number of button clicks you have to do in the old version, and the old version appears to be easier to get started, and that's why I kind of want to introduce you guys to that first in class, and then before I show you today 5.5, because it's just easier to get started in explaining what's going on. Okay, so that's what we'll do, and so we'll do a cantilever all three ways. Actually, there's four ways. There's analytical. There's this way, COMSOL 3.5. There's, oh yeah, we did it with sugar. And also there's COMSOL 5.5. Okay, so now this right here, the interesting thing, wow, this is still up since last week. Wow. No one uses the board? Okay, so the cool thing about COMSOL, even the new version, the old version, doesn't matter. The whole thing about FEA, finite element analysis, is that it's like a CAD tool. Well, it is CAD. So, but it's not just computer-aided design, but it's computer-aided engineering. Okay, does anyone know the difference between design and engineering in terms of computer-aided? Yeah.
Design is simulating the actual engineering process, but engineering is the actual execution of the design.
So the engineering part, now a lot of people will use CAD, computer-aided design, to mean the entire thing, but sometimes you might want to differentiate. Okay, for example, there are tools out there that just do the geometry, and that's all they do. For example, I think one website, I forgot the name, but you could design your house there, and you could turn it around in 3D. It doesn't do any physics, right? But you're designing things. Okay, so that is design, and also some people will think of design as tweaking parameters. Let's say you have a model already set up, and you tweak the parameters to optimize it. That's also a form of design. Okay, but when you get to engineering, that's more along the lines of doing the physics. So it's not just design, but you're actually calculating the physics involved. All right. So what do I want to say about that? Okay, so when you do computer-aided engineering or design in COMSOL, because you're dealing with FEA, typically you just start off with the geometry, and in this case, it's just a simple rectangle. Now, what does this represent, like right now? In COMSOL, it doesn't represent anything, it's just a shape. It doesn't know the physics yet. Okay? So when you start to model things in COMSOL, you have to define what that shape is. Now this is just a cross section. It's in 2D. I could do it in 3D as well, but it's just a cross section, right? And you guys have a guess. We're going to do cantilevers today, but COMSOL doesn't know yet that that's a cantilever. You have to tell COMSOL what the material is inside this and what is on the boundary. Okay, so these are the boundary constraints, and that's the subdomain. And typically in COMSOL, and that's why I like this version kind of like, so it has that up here. So this right here, it shows the boundary mode. So this has the boundaries. He has this one right here, this boundary, that one, the one over here, and this little thing right here. Now, I could have told you that this is not a cantilever, it's a hole in the board, and this is a material. But then what I would do, I would say that there's no physics going on in here. This right here is the material, and I could define what that material is. It could be liquid, it could be a solid, it could be gas, right? It could be the vacuum of space. This could be a conductor. It could be an insulator. I can make it whatever I want just by defining what the material is inside this box or outside and what the boundary conditions are. Okay? So in this particular case, this right here is actually, inside of here, is actually liquid. In this example, I'm going to do a cantilever in a second, but I just want to show you guys the difference that I'll make this a cantilever, okay? But I just want to show you first that it really is a liquid. We had an example like this a few days ago. But for example, let's say I want to go into physics. Because remember, I told you, physics is where you define everything. And it's nicely set up where I can say, I can go to the subdomain. It'll highlight that subdomain, okay? And it's highlighted. There's only one, and this subdomain is telling me this is following this equation right here. This is called, for people in fluid dynamics, is called the incompressible Navier-Stokes equation, okay? Pretty messy equation. Now, in COMSOL is actually based upon a very long PDE that has many parameters on it, many coefficients. And what you do is you turn certain coefficients off and on to make the equation you need. So in this particular case, these are the terms that survived. So these terms right here are on. There's lots of other terms that are useful for other types of equations, but they're turned off because that wouldn't be Navier-Stokes. So, so you could do that. You could make an equation that has every single term of basic physics, right, that you would normally encounter, and then just have some coefficients that turn off and turn on, and then you can make whatever type of domain you're looking for. So in this particular case, this has density, that rho right there, and it has dynamic viscosity, eta, right there. Okay, and you can see these parameters in this equation. Okay, but that, I could have multiple domains here. I only have one. It's very simple. Okay, but that whole domain, the physics is following, let me be clear, is following this equation. And that's what it's modeling. Okay, now let's get out of here, and then let's go to the subdomain, the boundary. Because remember, I told you there's subdomain and there's boundary. With everything you model, you define the subdomain and the boundary. So in this case, here's a boundary. And that's just the edges. Okay? So on this edge, let's highlight it. It says this boundary is the inlet. Okay? So something's coming in. And this boundary condition is velocity. I could change it. It could be pressure. But it's velocity. So something's coming in. And it's the inlet. I could make it a wall. I could make it an outlet. I can make it an open boundary, stress, all kinds of things. Okay? And this right here, this equation, is the velocity in the x direction. It's an equation. And so you could type in equations. It doesn't have to be just a constant value. are a linearly increasing value. It could be a pretty, nonlinear type of equation here, right? Now let's look at this other boundary. This right here, you probably guessed, is an outlet. Okay? So I can name it other things, but it's called an outlet. And the boundary condition, pressure, no viscous stress. All right? And the pressure is 0. All right, so now this boundary condition right here, this is just a wall, okay? And it's no slip. There's no slipping on that wall. Okay, so what that means in fluid dynamics is that the fluid that's right next to that wall has 0 velocity. Okay, it increases after that. It's sort of like this. Like if fluid is coming in this direction and going out this direction, the velocity profile sort of like looks like this. It's 0 right here, and then the velocity of the fluid is increasing like that the further you get away from the wall. Okay, it's a boundary condition. Same with this. This down here is a wall. I could make it an outlet if I wanted to. It'll simulate that physics. This right here, same thing. These are all walls. But these are just curved boundary conditions. But that's all it is. And look at the simple equation as following. Right? Very simple equation. Okay? But again, if I was trying to make a cantilever, this would not be a fluid. It would not be following Navier-Stokes. It would be following some other equation based on structural mechanics. And this boundary right here would be fixed. This boundary, all other boundaries would be free. And I would probably put a force over here or something like that. Okay, so now, again, you only need to basically deal with subdomain and boundary. There's other things over here you could do too, and we'll get into those later, but I just want to have a gentle introduction. So now this right here, plot parameters. Okay, so if I go to like general, it tells you all the kind of things it's plotting. It's going to plot a surface, and it's going to do particle tracing and geometry edges. So for the surface, I can go to the surface tab to say what is going to be plotted in that surface. The surface is like what's being shown on that plot. Here is the velocity field. I could select other things. I could select vorticity. I can select pressure. I can plot anything I want. Well, not anything, but what's available to me on this field right there in that subdomain. Let's check out another one. This is particle tracing. So if I go to the particle tracing tab right here, it's letting me know. Well, this is how it does particle tracing. It's a little complex, okay, but yeah, it's particle tracing, but it follows the fluid. I don't think the particles have any mass, but it does show you how the fluid is flowing, though. Okay, so it's like a point. It's like a point in that fluid, like a very zero mass particulate in that fluid. In that fluid. The other thing is go back to general geometry edges. So geometry edges, that's just plotting. It's just going to show the edges right here. Okay, so if I say apply, this is what it looks like. So it has solved everything. Oh, I should, before I forget, let me mention this. This right here, so this right here is the boundary mode. Remember, that's just the edges right here, the boundary. This right here is a subdomain. Remember, Navier-Stokes. This right here is a mesh, and it's showing how the mesh looks like. And you can define your own mesh. Now, meshing in COMSOL or any kind of FEA tool, it's an art. It really is. And let me give you sort of like a quick idea of what I mean. So, for example, if you were if you were plotting the number of elements here, yeah. And what I mean by elements, I mean all these little things right here are elements. They're finite. There's a finite number of them. I'm going forever, but they are finite elements. And what happens is that these points right here, those are the points where it's solving for these points, and all the lines, they are sort of like an interpolation between the points. Okay, so as the number of elements increase this direction, what happens is, how do I want to do this? Let's say it's sort of like this. Okay, and then this right here is like your relative error. Okay, in this direction. So if you have like one element, like if that's one element, and you're trying to show the how the fluid behaves, it's not going to be very accurate at all. It's going to be very poor representation. Okay, but that's a pretty fine mesh, so you're going to have a really good result. But what I'm trying to explain here is that there's typically, I call this a convergence knee. It's like a little knee, right? Because if you mesh going from 1 to maybe 10 to maybe 200, something like, I mean, well, 10 is in there somewhere. But as you increase, what happens is that you get a huge return on the relative error where that's going down. You want your relative error to go down. You want an accurate simulation. But then after a while, you pass this convergence knee, and let's say all you care about is an error at that level, okay, or this level. So anything below that is fine. I mean, let's say this level is like maybe the second, third, or fourth digit. So you don't care if the 7th digit or the 9th digit is accurate. You just want the first 2 or 3 digits. So that'll get you that. So any more meshing you do after that, you'll get more and more accurate or more refined, but it's not getting you. You have sort of like diminishing returns after a while, okay? Where what's happening here is that it's taking up lots of simulation time, right? And you may only get 1 extra digit of precision, and it may be more than what you really need. So it's always nice to know where the convergence knee is. And I don't know of a good way to do that. I've asked ComSol people, and typically what they do, they just refine the mesh to a finer mesh to see if anything changes. And if it doesn't change, then they reached past the convergence knee. So maybe in the future, something, some kind of algorithm can be done to deal with that. So anyway, so yeah, so back to this. So we apply. Here's the velocity field. Okay. Remember, I could change the surface to pressure and then plot pressure. See, here's pressure, the pressure field. It's moving around. It is animated. Oh, see, if I click the animate, you see all the times here? It starts from 0, all the way to like 7 seconds or whatever. And I plotted out the movie here. It's an AVI, but it's low resolution. I should turn the resolution up. But this was happening right here. Those are the particulates coming out to do tracing. And as you can see, if they get caught in blue, that's low velocity. If they get caught in the red, it's a higher velocity. This one is getting very close to the wall, and so they're slowing down. Because remember, there's no slip on the wall, so it's really 0 velocity if they get there. So very low velocity behind this little obstacle, very low velocity at the wall. Okay, so that's what that's all about. Okay, Now, um, like I said, I could turn this into a cantilever. Okay, so let's try that. Yeah, you have a question?
Yes. How do we place something down? I'm trying to follow along, but how do you actually place a component?
Oh, like draw it? Yeah, okay, that's what I'm going to do now. You read my mind. Okay, so what I'm going to do, I'm going to start from scratch, total scratch. So you can see how I'm going to make a geometry and plot it out. Okay, so COMSOL, that starts up. And so I'm going to select something new, and I'm going to, I can either go into the structural mechanics module, or I can go into the MEMS module. They both have the same, they have structural mechanics in MEMS, because MEMS, you know, has to have mechanics in it, right? And then I'm going to select on plane stress. Now, what these things are doing, each of these things, they are predefined equations. So you don't have to like type in Navier Stokes. Someone did it for you, and you just define the parameters and the geometry. Okay. So I just want this kind of like plane stress analysis. So I click OK. Okay. So now here's a blank thing. So if I wanted to do MEMS, you know, because we were doing some MEMS level kind of stuff, let me go in and change the grid access. Okay, so for this, let's just say, you know, this is 0 to 100. This is like the axis on like the X and Y axis. So it's in microns. So it's going to go from 0 to 100 microns. Let me turn my thing off. Okay, and let's go to my grid. It's all visible. And I'm going to have like partitions of like 2 microns each. And then I'm going to say OK. So every single dot you see is 2 microns apart. Okay?
I have a question.
Yeah.
You're doing that in 3.5, but we're in 5.5. Does anyone have 3.5? So
No.
I can't really follow along.
Oh yeah. So yeah. What I'm trying to yeah. So what I was saying in the beginning is 3.5 is easier to understand. So I'm just taking you guys through it as like a gentle introduction before we get to 5.5.
I have another question.
Uh-huh.
It's not working.
The what?
It's saying the license is not obtained.
Wait. So when you try to start 5.5, it says no license.
Yeah. It's saying the maximum number of reach.
Wait a minute. Wait. Does anyone else have that problem? Wait. Does anyone have it open? Oh, wow. Okay, I'll check on that issue. That's interesting. Okay.
I think next time we should come from 11 a.m. and then try to open it.
Huh?
Like come at 11 a.m., open it and then see.
Wait, I didn't hear what you said. I'm sorry.
Like I think next time I should come at 11 a.m. and then open it.
Oh, like come earlier?
Yeah, so I open it.
Well, see, that's now a good reason to get to class early, huh? No. It is interesting though. Okay, so, all right. So, I click on this rectangle right here, and then I draw, and you know that's all I do. Now they do have Boolean operations, so let me just show you this really quickly. Like I can have another shape here, and highlight them both, and I can do something like this, where now this is my shape, okay? So you could do Boolean geometry to make all kind of different kind of geometries. Okay? And I could leave it, it's fine, it's not a big deal. But anyway, so remember, next you want to define your subdomain and your boundary. Okay, so you go to subdomain, and there's only one of them here. So you highlight that, and then you can type in your Young's modulus if you know it. If you don't know it, but you know the kind of material, you could load a database of materials. Oh, and also if anyone wants access to this COMSOL, we can help out and get you access to this COMSOL as well. But we will be learning 5.5. So let's say you want to do semiconductors, and let's say you want this to be polysilicon. Okay, so once you do that, it loads up the parameters. So Young's modulus 160 gigapascals, Poisson's ratio, the density, thickness. Well, let's make the thickness like 2 microns. Okay, so there. So now this shape is now polysilicon. It wasn't before, now it's polysilicon. Next is the boundary settings. So in boundary settings, let's make this side fixed. It could be a roller. I could prescribe displacement. I could do all kinds of things, but I'm going to make it fixed. And then on this side, I'm going to make that free. Well, where everything else is free by default. Okay. But let's put a load over here. So I'm going to go to the load tab, and I'm going to select this side over here, and I'm going to give it a load. So if you do a side, your load is going to be newtons per meter. Okay. If you want like a point load, let me show you that really quick. You could do a point load where you go to point settings and just select a point, and it's going to apply a force just at that point. So let's try that. So I'm going to select a Y force, and let's say it's going to be 100 microns. Okay. And then I just press equals. If I press equals, it meshes it. So here's the mesh button. I can mesh it first, and that's what it looks like. I can refine my mesh by pressing this one, and as you can see, if I do that, you get a tighter and tighter mesh every time you press it. You know, and really, you know, you're worried about that convergence over there, but let's just do it this way. It's, you know, it'll be faster. But then just press equals, and then once you press equals, it'll plot it out. Now, this right here is stress is plotting. Yeah, one of the things with the old COMSOL is that it defaults to stress. The new one doesn't do that. The new one shows you the deformation when you're on strain. I mean, when you're on structural. So instead of doing, okay, so first what you want to do is show a deformed shape. So you go to your deformed, it's on, and then you can apply that. Wait a minute, why did it? This is supposed to be fixed over here. Okay, something happened. Let me check something out for a second. That's unexpected. Let me check my boundary condition. This is supposed to be fixed. Oh, it's free. I wonder why. Okay, it's supposed to be fixed. Not sure how that happened. There we go. Yeah, see? So remember, I have a force at this tip right here pointing upwards, and it's showing me the stress concentrations. And of course, you knew it was going to bend here a lot. And if I go into my plot parameters, I can say it's deformed shape. I can also, on the surface, instead of plotting stress, I can plot displacement and then apply that. And now what I'm plotting is displacement. Okay, blue is like no displacement. Red is the greatest displacement. Here's the color bar over here. So it says max. I mean the minimum and the maximum. Okay. So yeah. So that's how you do that for something that looks like a cantilever. I can also do it in 3D. So for example, let's say I want to do new. I don't want to save anything. Same old thing. I could, oh, wait a minute. I'm sorry. New, I got to choose 3D. Okay, so go to 3D. Okay, and then I could do structural mechanics. And then now I can draw like a cube or something, right? I can apply that. And now it's just a cube there. I could change the shape. It's 1 meter by 1 meter by 1 meter. I could make this 100 microns by 2 microns, or by 20 microns by 2 microns to make it similar in shape to the last one. And if I click apply or just OK, what? Something happened here. 100 microns. About 10 microns and 2 microns. Okay, so I can't see it because it's too small. It went from a meter down to the size of 1,000,000 times smaller. So this button right here is called Zoom Extents, and it just puts a large size. It fills up your screen with whatever size it is. So it went from a meter scale to micrometer scale. Okay, but as you can see, it's in 3D. Okay, and all you have to do is just click on the screen, and you can rotate it around. Now, if it's in 3D, same thing. You can do your boundary settings. Oh, and as you can see here, you have more boundaries now. Right, I'm cycling through all of them. There's 6 boundaries. This one's going to be fixed. Okay. I'm going to put a point over there. I'm going to apply that. I can go to my subdomain, and you can do it in any order. For my subdomain, it's still 1, and I'm just going to write in here 160 gigapascals. Okay, so I don't have to load it up if I want to. It also gives you the density, thermal expansion coefficient, things like that. And if I want to apply a point setting, I have more points. I can cycle through. These are all the points I can cycle through. I'm going to select this one over here, and then apply a load up in, let's see, in the Z direction. Let's say it's 100 microns. Okay, and then I can mesh it. I mean, I can show the mesh. If I didn't press the mesh button, then I could just press straight equals, and it'll mesh it automatically before it tries to solve it. Okay. But if you want to see the mesh, that's what it looks like. Now in 3D, the old version defaults to slices. These are slices of the stress. If I go to in here, I can go to slice. It's just 5 slices. I could put 50 slices if I want. So now you have 50 slices if you really want to see what's going on in there. Okay, but let's take off the slice plot and let's put on the boundary plot. So click that on, and then say you want to do total displacement, and that's what it is. Now it's not deflecting yet because deformation is not on. So let's turn deformation on and then press apply. So there you go. So it did deflect up, and again, this end right here is fixed. That is free and able to deflect. Okay. So now let's try the regular COMSOL. I mean the new version of COMSOL. And it's pretty much the same in terms of what you do. How you do it is different. It has a different GUI, totally different GUI. Okay. But as you can see, that's pretty straightforward. You have a subdomain. And gotta log back in. You have a subdomain and a boundary, and you set those kinds of things. Okay, so this right here is COMSOL Multiphysics 5.5. I got 3.5 right there. Now the reason I don't have any problem logging on is because I'm remotely logging into my office computer. Okay, so see, it's totally different. So let's say we want to do a cantilever, right? So what you do is first you click on. So some people can follow along, right? Okay. So first you click on the model wizard, right? And let's do it in simple 2D first. Okay. So but remember, just like last time, you could choose your geometry. You know, last time it was a pull down menu. Now they just show it like this. So let's click on 2D. And then it has this stuff like this. Does your version of ComSol, does it show these things right here? Does it show all of them? Oh, cool. Okay, great. So it has all these cool things right here. You could do heat, fluid flow, chemical, species transport, acoustics, AC/DC, some math. But let's do the structural mechanics. Okay, so we're going to highlight that. Remember, it doesn't know what physics you're trying to add until you add it. Okay? So now we're going to click the add button. Wait, how come it's not doing it? Oh, so solid mechanics and then add it. Okay, so after you do that, solid mechanics should end up right here. Okay? Because that's the mechanics we're doing. If we were doing something else like fluids, we would select the fluids. And also in another lecture, like maybe on Thursday, we'll combine two physics together. We'll do fluids and mechanics. So, and we could do this interaction type of thing, right, where it shows that the fluid is causing some mechanical cantilever to bend over. And we'll explore how to do something like that maybe. Okay, so then you do study. So, and let's say we just want to do stationary. This is the same thing as just like DC or static equilibrium type of things. Okay, so you click on stationary and then say done. Okay, now it has this screen. Not as intuitive, but like I said, there's many, many, many more options with the latest version of ComSol. And so it's much more, it gets really, really deep. Much more than on what I just showed you guys on the old version. Okay, so for geometry, so you right click on geometry. And let's say you want to build a rectangle. So you click the rectangle, and then you could define your width and your height. So let's say 100 microns for the width, and let's say height is going to be 10 microns, 10 e-6. So after you type in your geometry, then you could say build selected. Okay, and there it goes. See that? Okay. Now once you do that, then you can go over to materials. Then you can select your materials over here. So let's say you could do a search, which is really nice. That's not available in the 3.5. So like let's say we wanted to do silicon. We could like search for it. Then it'll show us where it is. And let's say we want to do polysilicon. And oh, what sidebar?
Just the one that you're the add materials one on the right.
Over here?
Open, you just right click on material, right, and then you can add from library, and it'll bring that window. Add from
Oh,
library.
okay, cool.
Sorry about that. Okay, let me just wait till you guys catch up to where we're at. Yeah, so I was like doing right clicks on these things right here. That's not the only way. Like for example, if you go along this right here from left to right, it's basically guiding you through each step of the process. You know, first you do some definitions. Like if you want to do some definitions like name a variable as length, name another variable width, and then you define that constant as that value. Then you do your geometry, you can sketch it, you could do your materials, then you do your physics. Okay? Okay, so yeah, so now let's go to mechanics. I'm going to right click on mechanics. Okay. And then I'm going to do a fixed constraint right here. Okay. And I'm going to let me see this. I'm going to click on this. And so this right here is going to be fixed. And so first, remember, it had like some kind of warning symbol. Now that's going to be fixed. Okay. Let's do another right click on this. And then let's do a let's do points. So let's do a point load. Just like we did last time, a point load. But this is a different way of doing it because this is like a different version. So let's do a point load. Is down here. It has that exclamation mark on it, right? Until I come over here and I click, a point load. Right. Wait a minute. And then let's say this point load, y right here is going to be 100 micronewtons. Hope I didn't say 100 microns before. Okay, then once I do that, then I can go to study. Study is like doing the doing the equal signs. So once you press study, then this middle section changes to the thing where you can compute. It's the equals. And so you can press the equal sign, and then it'll mesh it for you, and then plot it out. And as you can see here, it starts off with the deflection, unlike the older version. Okay. So yeah. Now, as you can see here, there are lots more things you can do. And I hope you can see what I was talking about before, where even though you haven't seen either tool before, the 3.5 has like, it seems like a little easier to deal with because you don't have so many possibilities, right? But, we'll learn this way, learn this version, and we'll get into depth with many other things that it can do. And we'll go from there. Does anyone have any questions about this example right here? Yes.
Can you import CAD files?
Huh?
Can you import CAD files?
Oh, yes, you sure can. Of different types as well. And you can also export different kinds of formats as well. Yes.
I don't think the material set properly. It's telling me that I don't have the Young's modulus for this linear elastic integer. Yeah, I don't.
Yeah, do you still have an exclamation point? Yeah, the little exclamation points are like little warnings telling you, hey, something's not set yet.
Yeah, I have that. Selection is 19.
Yes.
Two computers don't have console.
They don't have console at all?
Yes, sir.
You picked a really bad seat. No. Really? Okay, so, huh?
I'm not able to open it.
Well, yeah, yeah. So I know we have a limited number of seats, but I thought we had enough seats. I wonder if now this is they have pushed ComSol to two rooms. This room, and also there's another computer room over in ECE. So there's no constraint on just students in this class logging on and using ComSol. Like, for example, if a lot of students went over there right now, start using ComSol before you guys got on, they'd be taking it up. So but again, once we get ComSol, we'll solve their problem. So
It's on this one.
it's on that one? Okay. Wait, were you able to log on and get it? Because he can't.
I know it's starting up.
Is it starting up?
We'll see. Because it's just loading up right now.
Were you able to load up in yours?
No.
Wow. Now, if his starts, then maybe it's not a is another issue.
Same right now.
Huh?
It's the same message now.
Oh, he has the same message now. Oh, okay. Yeah. Okay. So we have more people on ComSol than we have.
Maybe they are just putting 20. But
Huh?
there are 20 students in the
The-
like there are 20 students in the classroom. Maybe they only have 20 available at home.
Well, they told me they have 30, and it looks like less than 30 in here. So my guess is that there are other people on campus using ComSol right now, using our ComSol that I got for this class. So now there is one way around that, where we could buy another 30-seat license. It's only $7,000. Yeah, no. Small dip in the bucket for Auburn, right? A lot for us, but.
Will that impact being able to buy those other like add-ons?
That's a really good question. I don't know. I think not. I think not, but I don't know, but probably not. But yeah, if we continue to have this kind of problem, I will let the department know, the department chair know that the other problem we're having, and the only solution I think they'll do is like either buy another license, which is like I said, drop in a bucket for the university, or they may say, hey, the class is being recorded, so so if someone doesn't come to class, they can easily watch it and do the same thing later on during the day. But I don't know. Okay, so are there any other questions with this? Okay, great. So what we're going to do, we're going to end the class early today, only because I have a proposal due this evening. So I got to hurry and finish up with that. So see you bright and early on Thursday so we can get our seats, get council going.